Is on finding kinetic energy. So you may remember from our bubble map that there's lots of different kinds of energy, and energy of motion we called kinetic energy. So this is energy of things that are in motion. That included things like heat and wind and stuff. But anytime something's moving, it has energy because it's moving, and it can do work for us. If you had a whole bunch of bowling balls rolling down a lane, you could somehow harness that energy to do work for you. You could make a generator from that or something. So anytime something's moving, it has energy because it's moving, and we call that the kinetic energy. All right? So here we have a bowling ball. It's zooming down the lane. Because it's in motion, it has energy. It can do work. And how much energy it has depends on a couple things. First of all, it depends on how heavy the bowling ball is. Heavier bowling balls have more energy. It takes more energy to get them going, and they have more energy to give us when they smack into things. So not only does it depend on the mass, it also depends on the speed, on how fast they're moving, which we called velocity. So it turns out that when you do some complicated physics, you can show that the kinetic energy of an object in motion looks like this. So this would be a good thing to put in your toolbox. This is an equation we're going to use. So far in your toolbox, you just have a conversion from calories to joules. But this is how we're going to calculate the kinetic energy of something when it's in motion. So take a minute, you can pause the video if you want and write it down. The kinetic energy is 1/2 the mass times the velocity squared. And remember from math, when something is squared, it means times itself. So we'll look at that in our example problem in a minute. In your toolbox, write down what these things mean because you might forget later. So anytime we're calculating kinetic energy, we have the kinetic energy, we have mass, and we have velocity. So those are the things we are going to look for when we solve a problem. So here's an example problem I want to solve. I've got a skater, and she has a mass of 80 kilograms, and she's moving down the street at 3 meters per second. So we're talking about 8 or so miles an hour, but it's 3 meters per second, okay? And I want to know how much kinetic energy does she have? That's the problem I want to solve. So to solve this problem, I'm going to draw myself a little skater here. So we're just trying to make a diagram. So here's my skater standing on a skateboard, and she is moving down the street, okay? And because I'm trying to find kinetic energy, I know I'm going to have kinetic energy, I'm going to have mass, and I'm going to have velocity. So when I read the problem, I'm trying to find those things, okay? So the problem says a skater has a mass of 80 kilograms. So that's going to be 80 kilograms. And she is moving down the street at 3 meters per second. So this is going to be 3.0 meters per second. That's her velocity. And it says, what is the kinetic energy? So I'm trying to find the kinetic energy. Okay? So to solve this problem, we are simply going to use our equation, which says the kinetic energy equals 1/2 the mass times the velocity squared. I'm going to put in my numbers. So the kinetic energy is going to equal 1/2 of the mass, which is 80, times the velocity, which is 3.0 squared. Now, you can do this all at once on your calculator, or you can do it in 2 parts. It helps me sometimes to break it up into 2 parts. I'm going to take 1/2 of 80, so on your calculator, that's 0.5 times 80, and that's going to give you 40. And we've got to multiply that by 3 squared. So remember, squared means times itself. So 3 times 3 is 9. So you're going to take 40 times 9, which, when you plug in your calculator, is 360. And since this is energy, that's going to be in joules. So the kinetic energy of the skater is 360 joules. All right? You see how I solved that problem? So you can use that as an example. To find the kinetic energy, you got to take 1/2 the mass times the velocity squared.